Alright, welcome back guys again, and now we will again continue our reading of this paper. Okay, and we already read it till here, I think. Here, right? HLC is backward compatible with okay, right? Then we are we are here. HLC provides masking tolerance to common NTP problems, including non-monotonous time updates, and can make progression capture causality and information even when the synchronization has degraded. Okay, HLC is also self-stabilizing, fault-tolerant, and its reagents are arbitrary corruptions. It's resilient to arbitrary corruptions of the clock variables as we discussed in section 4. Okay, let me copy this and go for our explanation. Can you explain this in simple language and in brief? Right. So this paragraph is basically saying that HLC is robust even when NTP has problems. Like events, NTP also can drift, right? So HLC provides masking tolerance to common NTP problems. Simple meaning of this is if the NTP clock has problems, HLC can hide or mask those problems and continue working. For example, if NTP suddenly goes backwards, right, from 10.06 to 10.05, went backwards. So in this case, HLC uses its logical part to prevent this from breaking event order, right, and can make progress and capture causality even when synchronization has degraded. Suppose block A node A clock is 10 and node B clock is like 2 milliseconds behind, right? So HLC does not simply stop here, right? It can still maintain E happen before F relationship. So it can continue processing events and preserve the cause and effect information. Okay. Even if the synchronizer has degraded, and HLC is self-stabilizing. Self-stabilizing means here, even if something goes wrong with HLC's internal state, right, the system can eventually recover by itself and return to correct state. No manual reset is required. How? Right. Fourth is, it is resilient to arbitrary corruption of clock variables. Like imagine HLC variables accidentally become like this. So because of some fault tolerant memory corruption, right? So HLC algorithm can even eventually correct itself by system continue running. Okay. It stabilizes because HLC continuously compares its logical timestamp with the current physical NTP time and updates itself, right? Very simplified. Suppose HLC has two parts, HLC physical part and logical part. Imagine it gets corrupted. Current NTP time is 100 and logical part is only 7. That means corrupted. When the next event happens, HLC checks the physical clock, which is 50, NTP is 100. 50 goes out, it moves the HLC forward to the consistent current physical time, like 100 or something. Think of it as an anchor, like NTP physical time, HLC logical continuous corrected. Okay. Alright, and yeah, next part here it is this. It is also, they are also saying like we implemented HLC and provide experiment result of HLC deployments under various deployment scenarios. Okay, in section 5 we show that even under stress testing HLC is bounded and the size of the clocks remain small. Okay, these practical bounds are much smaller than the theoretical bounds proved in our analysis. Our HLC is implementation made available in an anonymized manner at github.com/augmented type project. Okay. Uh, I think this is very simple to read, but okay. Let's if it is a ritual, then we can follow it. They actually wrote the HLC algorithm software, so it is not just a theoretical idea. And provide experiment results under various deployment scenarios. They tested HLC in different situations such as normal, network stress, different deployments, heavy workload also. So they wanted to see how HLC behaves in practice. Even under stress testing, HLC is bounded and small. The clock sizes remained small, right? So they really put HLC under very stressful conditions. Even then, HLC size was remained small and doesn't grow uncontrollably. So this is important because a clock that keeps growing, right, would eventually consumes lots of memory, right? Okay. So HLC is even better in practice than the mathematical worst case analysis suggests. Alright. HLC is even better in practice than the mathematical worst case analysis suggests. Okay. Implementation is made available. Okay. So we look at our sources expected. Okay. And next thing is the HLC has direct application in identifying consistent snapshot and distributed databases. Okay. 256. It is also useful in many distributed system protocols, including causal message logging in distributed systems, Byzantine fault tolerance protocols, and distributed debugging, distributed file system, distributed transactions. Okay, in section 6, we showcase the benefits of for snapshots, read and distributed databases. Okay, I think I can do all this also now. First of all, preliminaries. Then we have logical clause, problem statement. The description of the naive algorithm, HLC algorithm, it is here. Okay, theorem 1, theorem 2, these are the theorems, I think. Total properties of HLC, resolution of HLC results, okay, and these are some results here. Statistical evaluation. Alright, snapshot, conclusion, and then. So we are approaching the algorithm here. We will learn some algorithms today. Alright, so then we go forward after that. Yeah. So as we can see like direct applications. Just I am reading it just to read, right? It will not take this much time. You explain this in simple language and in brief. Right. So this paragraph is saying that HLC is useful in many real-world distributed systems. Consistent snapshot means what? HLC can help a distributed system take consistent snapshot. A snapshot is give me a state of whole database as it existed at a particular time. So HLC helps ensure that the snapshot doesn't contain impossible states, right? And other uses of HLC, like impossible state means like the event E happened before F, but timestamp of E is larger than timestamp of F, right? It is impossible state, right? So snapshot should contain only the possible states or events, right? Other uses of HLC is causal message logging, record message while preserving cause and effect, and Byzantine fault tolerance that helps system deal with fault and malicious nodes. Okay. Alright, it is also helping that, and distributed debugging, understand what happened and in what order, right? And distributed file system, like order changes to files across machines. And order transaction operation and transaction across different machines. Okay, snapshot reads, the paper particularly focuses snapshot reads in distributed databases. So many the database at it looked empty. Okay, whatever. Preliminaries, a distributed system consists of a set of nodes, okay, whose number may change over time. That is correct. And each node can perform 3 types of actions, right? A send action, a receive action, and a local action. Alright, the goal of a timestamp algorithm is to assign a timestamp to each event, right? We denote a timestamp algorithm with an all capital letters name. The goal of timestamp algorithm is to assign timestamp to each event. Okay, we denote a timestamp algorithm with a all capital letters name. Okay, and the timestamp assigned by this algorithm by the corresponding lowercase name. Okay, so the algorithm will be capital letters, and the time assigned by this algorithm be the corresponding lowercase name. Okay, for example, we use LC, logical clock, right, to denote the logical clock algorithm by Lemper, and use LC.E to denote the timestamp assigned by event E is by this algorithm, right? This has the notion of happened before. HV captures the causal relation between events in the system. Defined in 12, event E happened before F denoted by H happened before F is a transitive relation that respects the following: that E and F are events on the same node and E occurred before F. So when we say that E happened before F, we are talking about the same node, right? Or E is send event and F is the corresponding receive event. If it is in different nodes, then E happened before only if, then E is the send node event and F is the corresponding receiving node. So we say that the E and F are concurrent or denoted by E concurrent like double pillar F, if and only if either E does not happen before and F is not happened before. If there is no relation between them, when there is no relation between them, when is because like when there is no relation between them, when they are neither E happened before F in the same machine, nor F happened before E in same machine, and E didn't send anything to F, or F didn't send anything to E in different nodes, right? So based on the existing result in the literature, the following are true, right? So logical clock E is equal to logical clock F. That means they are concurrent. if E happen before F, then vector clock of E will be less than vector clock of F. However, the following claims are not true. Like E happen before F, right? Alright, let me go with it first, then alright. These are just very. Can you explain this in simple language and in brief? Alright, so it is what? This paragraph defines basic setup and terminology for distributed system. A distributed system is a collection of nodes, computers. You can see node A, node computer A, computer B, computer C, and the number of nodes can change over time. Each node can perform three kind of actions. Local action happen inside the node, right? So like calculate is something like that. And send action send a message. A node send a message to B. Receive action like B receives the message, right? So timestamp algorithm is a timestamp algorithm gives every event a timestamp. Like event E timestamp of this is 5, event F timestamp of this is 8, like that, right? So different algorithms can assign timestamp differently. That is true. For example, LC lamp logical clock, hybrid logical clock. If LC gives event E a timestamp, we write LC dot E as 5. Happen before means we know that one event happened before another because there is a causal relationship, right? There are two basic cases. Same node, like E happened before E, since E happened before F on the same node, right? E happened before F. Send, receive. Like E sends something and B receives something. A message must be sent before it can be received, right? Therefore, HFF, right? Happened before F. Transitive, each E happened before F and F happened before G, then E happened before G. This is called transitivity. Concurrent events, two events are concurrent if neither happened before the other. So E is concurrent to F. Mathematically, E happened. Okay, for example, E happened X, F happened before Y. Then A and B haven't communicated, so we may have E concurrent F. We simply cannot say that E caused before F or caused before E, right? But I have a doubt here. How we can say it? So we say E happened before because both events happen in the same node, and node executes its events in a definitive sequence. For example, E read data and the calculate the result. Node cannot execute F because E execute E in the sequence, right? Therefore E happened before F, so we write E happened before F. Why? Because the definition of happened before actually says E and F are events on the same node. Important distinction, we are not saying the physical clock proves it. We know it from the execution order of the node E F. Therefore, SF. This is exactly what logical should capture. What if E and F are independent? If E is independent, then neither event causes the influence to the other. That means E, no communication. We have not E and F, a definition variable. If A and B are not communicating, we can say concurrent does not necessarily mean happen at exactly the same time. If E, G, F, and E and F are dependent, is this state possible? No, if by independent you mean no causal relationship, then E and F are independent cannot be true. The revision are opposite. If E happened before, this means E causally happened before F. So there is a causal relationship, right? And if E independent, then neither causal influence the other. So E happened before F, therefore false. Alright. Then here we have based on this and it's a two-sided paper actually. So the main idea about what each clock can guarantee, right? First remember, E happened before F, E definitely happened before F, and E and both are concurrent, no causal relationship in this case. So claims that are true, E happened before F, that means logical clock of E and logical clock of F is less than F, right? If E caused proceeded to F, then Lamport clock guarantees E happened before F, right? That is true. Here, if Lamport clock of E and Lamport clock of F are equal, then they are concurrent. If two events have the same Lamport timestamp, they cannot have the happened before relationship, right? 5 it always by concurrent. E happened before F. This is a big advantage of vector clocks, right? So E happened before F, then vector clock of E is less than vector clock of F. For example, a vector clock of E 2 1 F 3 2. Since every component of E is less than equal to corresponding component of VF, and at least one is smaller, therefore as E happened before F. Okay, claims that are not true. That E happened before F. So this says logical clock of E is less than logical clock of E. Then E must happen before F. This is false, because for example, a logical clock of F. This will not imply that, because logical clock of node A5, suppose E and B never communicated, right? So it will not time will not say it, okay? Then logical clock of E, logical clock of F, but there is no causal relationship, so concurrent. So we keep on. Lamport clock gives a sufficient condition for causality, but not the necessary one, okay? And logical clock of E is equal to, this is also false. This says if E and F are concurrent, then Lamport clock time must be equal. That is not true, because false concurrent events can be different logical clock values also, like they never communicated in this case. Then next thing, E happened before F implies physical time of E is less than physical time of F. This says if E happened before F, the physical time stamp must be always be ever. False, because physical clocks on different machines may be not be perfectly synchronized, so that is not also true, right? The easiest way to remember, like Lamport clock LC, what it guarantees E happened before F, then, right? That will imply that clock thing, right? Vector clock E happened before F, then it will imply this, okay? Real time actually not guarantee causality. That is true. And next thing, what we HLC hybrid logical rules. In this section, we introduce our HLC algorithm, starting with a naive first solution first. We then prove correctness and tight bounds of an HLC. We also elaborate on the useful features of the HLC of our distributed system. Okay. Here, and the goal of HLC is to provide one-way causality detection similar to that provided by LC. By maintaining the clock values to be always close to physical NTP time, the formal problem statement for HLC is as follows. Given a distributed system, assign each event E, right, a time stamp N E such that I will break. It was just a minute. Alright, the goal of HLC is to provide one-way causality detection similar to that provided by the logical clock. Alright, so this is the goal of this SLC clock. While maintaining the clock value to be always close to the physical NTP clock. That is also true. The formal problem stated for SLC is as follows. You have given a distributed system, assign each event E a timestamp L dot E such that E happened before F, then it should imply that timestamp of E must be less than timestamp of F. Alright. The space requirement for LE should be order of 1 integers, and L dot E is represented with bounded space. Okay. L dot E is close to PT. Physical time of E is that, like logical time of E minus physical time of E, difference of this, it should be bounded, like there should be a boundary, it should not be more than that. Okay. First requirement captures one-way causality information provided by HLC. The second requirement captures that the space required for ID is order of 1 integers. Okay. To prevent encoding of several integers into one large integer, we require that any update in LOT achieved by order of 1 operations. The third requirement captures that the space required to represent L is bounded. It does not grow in unbounded fashion. In practice, we like L to be size of PT of E, which is 64 bits in the NTP protocol. And finally, the last requirement states that the LOT should be close to PT. This enables us to utilize SLC in place of physical time. Okay, let's understand this more detail. Alright, let's go through here. This also now. And then go through this. No. Problem statement. Here. Okay. Can you explain this in simple language and in brief? This is the main goal of HLC. Let's simplify it. What is HLC trying to achieve here? HLC wants to combine two important properties. One is logical clock, the causality E for F, and physical time, real time, what time, right? So the goal is HLC should preserve causality like logical clock while staying close to real NTP time, physical time, right? This is the main goal of it. So, four requirements. One is preserve the causality. If S F E event before F, then HLC must guarantee that timestamp of E must be timestamp of F by the HLC, right? So if E caused F, the HLC will never reverse their order. They use only constant space. Like HLC timestamp should need only fixed small amount of integers. HLC is equal to physical part plus logical part. That's just two integers, regardless of the whether they are 10 nodes, 1000 nodes, or like 100,000 nodes. Okay, so space is order of 1. This is a major advantage over vector clocks. Okay, when space grows with number of nodes. Timestamp size must remain bounded. Also, the timestamp should not grow forever, like 1, 10. Okay, then this is the value of timestamp. The number would eventually require more and more bits. In that case, so HLC wants timestamp to remain within a fixed number of bits. Ideally, HLC is equal to 64 bits. Very similar to NTP timestamp. Okay. And number 4 requirement is stay close to physical time. HLC should not drift far away from the actual clock. Ideally, physical time is equal to this, and HLC is this. Not like okay, with a 5-second gap, right? Mathematically, they want HLC minus like bounded values. Difference between physical time and HLC time for a particular event should be less than or equal to a bounded value, right? So HLC remains a reasonable replacement for physical time. See why all 4 together? The author wants logical clock, causality, physical time, correct plus practical. Right. Alright. Next thing. To illustrate this, consider the case where the designer wants to take a snapshot at a physical time t. Okay. Given that physical clocks are not perfectly synchronized, it is not possible to get a consistent snapshot by just reading state at different nodes at time t, as shown in figure 2, because there is uncertainty interval also in that case, right, in physical time. On the other hand, using ALC, we can obtain such a snapshot by taking a snapshot of every node at a logical time t. Such that snapshot is guaranteed to be consistent, because from the HLC requirement 1 we have this, right? In section 6 we discuss it in more detail, how HLC enables users to take a posteriori consistent snapshot of the distributed system. So this is, I think, some naive algorithm, I think, right? Initially, logical clock of J is 0, send or local event. Logical LC of j is base of L of j plus 1 plus physical time of j. Timestamp with Lj. Receive event m. Lj equal to max of Lj plus 1 plus comma Lm plus 1 Pt of j. Timestamp with Lj. Nav adjustment for node j to take uncoordinated. Okay. Okay, let's understand the description of the naive algorithm first. Okay, then we will also learn this, right? Given the goal that L dot E, logical timestamp of event E, should be close to physical timestamp of E, right? In the naive algorithm, we begin with the rule for any event E, right? Logical event of E must be greater than or equal to physical time of E. Why? We can see because we want to escape the uncertainty interval also. We design our algorithm as follows in figure 3. Where is figure 3? It is figure 3. Yeah, I think figure 3 it is. This algorithm works on similar to logical clock. Initially, all the L values are set to 0. When a send event say F is created on the node J, we just set L or F to be max of whatever the logical time there plus 1 or physical time of J at the node. So whatever the max we will set there because we want to be close to physical time, right? Where is the previous event on node J? right? Okay, so we are talking about if e logical event of e plus 1 is having greater value than physical time of j, then for f we want to be close to this. Okay, right? This ensures that L is less than L of f. If it also ensures that logical time of f is greater than or equal to physical time of f. Likewise, when a receive event f is created on the node j, right, then logical time is set to max of logical event of e plus 1, comma logical m plus 1. What is m here? We will see where L dot is time from a previous event on j. Okay, on the node j, right? And L of m is the timestamp of the message, and hence the send event. Okay, of the L of the send event. Okay, this ensures that L of e is less than L of f and L of m less than or equal to L of f. Send event must be less, and both are less, right? It is easy to see that the algorithm in figure 3 satisfies first two requirements in the problem statement. However, this naive algorithm violates the fourth requirement, which also leads to violation of the third requirement for bounded space representation. To slow the violation of the fourth requirement, we point to our counter example in figure 4, which shows how difference between logical event e minus physical time of e grows in an unbounded fashion. This messaging loop among nodes 1, 2 and 3 can be repeated forever, and at each turn of the loop, the drift between logical clock and physical clock will keep growing. The root of the unbounded drift problem is due to the naive algorithm using L to be maintained both the maximum of physical time value since you pattern the logical clock increments from the new events. This makes the clocks lose information. It becomes unclear if the new L value comes from PT keep HLC close to physical time, okay, but whenever causality requires it, move HLC forward. Basic rule of it is for every event E. Logical time of E must be greater than physical time of E, meaning HLC time should never be smaller than the physical clock. Okay, for a normal or send event, suppose the previous event on node J has timestamp L dot E, right? For new event F, L of F logical timestamp F must be maximum of LE plus 1. Why we are adding 1 here? Because we want greater than this and physical time. So it will be greater than equal to this physical time of G, right? So it should be whichever is larger in this case. LE plus 1 keeps the logical order and this keeps the HLC close to physical time. For example, previous HLC is equal to 100, physical time is 105, then it will assign it to 105 here. But if the HLC is 100 and physical time is this, then in this case it will assign it to 101. So HLC moves forward when necessary, right? For a receive event, suppose node B receives a message from A. Previous timestamp at B plus 1, right? Timestamp carried by the message plus 1 and B is physical clock. So this timestamp at B of event E plus 1, message send event plus 1, physical time plus 1. Why 3 values here? Because B is previous SLC is 10, let's say message SLC is 20, right? And B is physical time is 15. So this must be 21, right? The causality is preserved. Core idea HLC for new event. Right, this is a naive algorithm here. You can see here also. Send event, receive event at local. Okay. Now right, and then we have this. So this is a counter example. So 0, 1, 2, 3, these are I think 3 nodes, 4 nodes. Physical time, it is logical time, 10, 10 here. It sends some message here, 1, 11. Logic physical time is 1, 11 is the this. The next event it created 2, 12 plus 1, right? So here it was 2, 13, 3, 14, here 4, 16, 4, 17. Okay, let me okay. Okay, let me keep this this part only for now, right? Understand this part, then move forward. Yes, the problem is that the NAB HLC can keep growing, moving forward because of message even physical time is not moving much. Hmm. Okay, so hmm. So what happens? To recall the receive rule, right? This naive at Chelsea can keep growing for because of the messages. Use of the messages, even when political time is not moving much, so the difference will continue. What happens is recall the receive rule. We have this rule like event in the receiving node and message event timestamp of message like send event and physical time at that particular node j. Suppose physical time is around 100, but the message carries a logical time of 200. Receive this is 201. F we have assigned f2 because it must preserve the causality, right? Now imagine the node keeps sending message in a loop. Node 1, node 2, node 1 and again sending node 2. Each receive adds plus 1. 101, 102, 103, 104. But suppose physical time remains around 100. So then the difference becomes L minus P first loop 1, then 2, then 3, like this. Right? So the logical clock can drift arbitrarily far ahead of physical time. Okay, so it was 201, right? So 101. It was 200 actually. Okay. We cannot like change the physical time, right? So physical time minus L logical time. L of event E is increasing. Requirement for fields HLC is not guaranteed to stay close to physical time. Requirements for some may need more inputs. Okay. Now algorithm is too willing to increase the logical clock because of repeated messages. The message loop can push HLC forward forever if even if physical time isn't caught up. Alright, that's understandable. And here we have to understand this also, guys. Right. So V here. And this is and this image we have to give also. Learning this in simple language and in fun. So yes, this is explaining why the naive HLC algorithm fails and why the authors needs a better algorithm. What is the root problem? Naive HLC uses the same value L, okay, for two different purposes. L is equal to maximum physical time seen plus logical increments needed for causality. So after some events, if we see L is equal to 17, we don't know why it became 17. Is it because of the physical time? Is it because of the logical increments? We don't know, right? Was it because physical clock was 70 or because causality forced L to increase to 17? This information is lost in this case. So why can't we simply reset L? Suppose L is equal to 100 and physical time is 10. You might think 100 is too far ahead. Let's reset L back to 10. Right? But this can break causality. Suppose a message carries as 100 and receiver reset it to clock 10. So then we could get send is 100. We need causality resetting and changes. Okay. Why does figure 4 demonstrate the node keeps sending message in loop, node 1 like this? Each message forces the receiver L to increase 11, 12, 17, but the physical clock doesn't increase fast enough. Therefore, PD keeps getting larger. For example, PT was 4 and L was 17, like 13 here. Continues to 13, 20 like this, it will become unbounded. What about making the physical clock increase by at least 1? You might think just to make sure physical time increases between every event. The author says that still isn't enough. Figure 4 already satisfies this condition, but the logical part can still increase faster because messages repeatedly propagate a larger L. Okay. When would the naive algorithm code actually work? This is a strong condition. Every send and receive must take enough real time so the physical time increases by at least 1 during them. Then physical time can keep catching up with the logical time. For example, logical 10-11 like this. The gap stays bounded. But this is an unrealistic assumption because in real distributed system events can happen much faster than physical time advances. The main idea in algorithm has a fundamental problem, physical time, logical time. It put both pieces of information to one number, so it cannot tell what value come from. Okay, that's it, guys. Alright, and here physical time is 10, logical time is also 10, right? It goes here. 1, 11. Logical time is 11. Physical time is 1, 2, 13, 3, 14, 3, 15, 4, 16, 4, 17. I don't understand this figure actually. This figure is very confusing. What is 0, 1, 2, 3, 4 here? Okay, it is saying okay. Root on 1 directs from due to the naive. So far, the logical function from the events, logical relationship. This makes the clocks important. It becomes unclear okay. As in the message from node 0 to 1 or from causality. So at node 0 physical time is the 10 and logical time is also 10. At node 1 physical time is 1 and logical time is 11. So what they do, and this is logical time, physical time is 2, 12. At this time they send a message of 2, 13 was there, and 3, 14 at it they send a message, right? And it increasing for 16 to message, then this message for 16 becomes for 17 here, right? So you see we forced the logical time to be 17 here, while physical time is only 4. So there is a huge difference, right? 470. Even when we were trying to increase at every step, right? From the physical times and all, because different machines can have different physical times in that case. Okay, HLC, all problems in computer science can be solved by another level of indirection. David Wheeler. Okay. So thank you so much guys. We will look into HLC algorithm later, and thank you so much for watching.